our current direction times my Hessian matrix times my dk plus minus 1 equals to 0. So what does that mean? That means dk and dk minus 1 are Hessian k orthogonal. So just like the concept of Q orthogonal. But remember, when we derive, our Q is Hessian. So we wish our current moving direction is having H orthogonal with the previous direction. This is what we wish. Okay? So what's next? Let me see how I can make this cleaner. dk times gradient f equals to 0y. Let me see how I could make it a simpler derivation. Two. Okay, I think I need to collect them. Okay, to do further, we need to again revisit the second order Taylor expansion. Okay, so let's revisit in this way. My function f, this time I write it down in this way. Fk plus 1 is close to Fk plus x k plus 1 minus xk dot product gradient fk plus 1/2 xk plus 1 minus xk dot product Hessian k dot product xk plus 1 minus xk. Right? So basically, this is exactly second order Taylor expansion, but we are studying what's the f at this is basically f and using x k plus 1 plugging in, right? We want to know what would be the approximate function value of this. And all our variables are here, x, k plus 1, k plus 1, k plus 1, and treating previous design as our expansion point. Expansion point. And expansion point plugging in here, expansion point plugging in here. And also expansion point plugging in there. So this is a Taylor expansion that we always use. Over here, we need to rewrite something. dk dot gradient f plus 1 equals to 0. Why is that? gradient. Let me see how I could get one of the equation right there. Oh, okay. So recall this equation. Recall this one. Copy. So paste. Recall this one. Oh, actually not this one, the other one. This one. Copy. Delete. Paste. Recall this one. Okay, this is what we had earlier. So over here, we could actually do some plug-in. Because we have xk plus 1 minus xk. Same here. Same here. And we have xk plus 1 minus xk over in the previous equation. So we can rewrite the above equation as the follow. Fk plus 1 then equals to fk plus alpha k dk dot gradient k plus 1/2, and because we have two alphas, so alpha k square times dk dot Hessian k dot dk. So we will have some new equation like this. Okay, and again we can do something further for the purpose of derivation. Let's try to do derivative against alpha k and see what will happen. Okay, let's do this. Because alpha k is unknown, right? Alpha k right now is like a variable. So if we do this, the only alpha k is right here and here. So when we do that, the remaining part becomes d dot gradient fk plus 2. There's no more 2, but 1 alpha k, and then dk plus. We have something like this. Okay, and we could merge them together into the following form: dk dot gradient fk plus alpha k times Hessian k dot dk. So this will be used later on. The derivative of fk over alpha k. So let me look at from what one is. Okay, so now let's see if we can do derivative, do a gradient operation. do a gradient operation against f, see what will happen. So if we do that, this becomes gradient f k plus 1 equals to, the first term become constant. The second one, we have the gradient left. And then finally, we have Hessian dot xk plus 1 minus xk. Okay, so this is what we have if we do a gradient operation. Okay, and again, over here we can replace this. So because of this equation, we can rewrite as alpha xk plus alpha k Hessian k dot dk. So just plug in. Just plug in. Okay, so many equations look alike, but this is necessary. Now, because we wish to have optimal, so no matter if you are doing derivative with respect to alpha, or if you are doing gradient with respect to your x, you wish this become 0. So you wish these are 0. Now, here this one, you wish df k plus 1 d alpha k equals to 0. So you have this. You wish that is 0. You wish that is 0. Let me see. Just oh, so but the interesting part is this guy is actually what's inside this, right? Gradient f k alpha k Hessian k dot product dk. So this is exactly that. And so this is basically here. And you wish this one should be 0. So what you will get is actually dk dot gradient fk plus alpha k Hessian k dot dk. And this is actually dk dot what? Gradient f k plus 1. So this is actually 0. Okay? So what can we do with this? Where do we have that? dk, okay, now we need to recall this guy. So recall this. So over here, of course, when we have index plus in 1, the whole equation supposedly will satisfy the same rule. So we can have dk plus 1, of course, must be equals to all the index plus 1. This, of course, needs to satisfy as well. Okay? And now we will do several things. we oh, this is a very long derivation. Sorry. So if we have this, we can do post multiplying. So we use this to have a dot product with HK and then DK. Okay, let's do this. A post multiplying, post multiplication. So you multiply, you do dot product on the right hand side of it. Okay. So if we do that, we should do the same thing to every term. So we will have this plus alpha k dk so we are doing exactly same thing to every term here. Okay, so what's interesting is that since we have dk plus 1 dot hk dot dk, and we know dk and dk plus 1 should be h orthogonal. So this term becomes 0. This is 0. Because they are, because dk and dk plus 1 are hk orthogonal. Okay? So with all those effort, we finally can rewrite something like this. Beta k equals to gradient f k plus 1 dot hk dot dk over dk dot hk dot dk. And remember, at the beginning when we start to derive this whole thing, starting from steepest descent. Right here, when we start some trial formulation based on steepest descent, we said xk plus 1 equals to fk plus some unknown alpha times some moving direction. And each direction equals to the negative gradient plus some unknown update times the previous direction. So now we said we don't know alpha k, we don't know beta k, but we don't know beta k. So we need to figure out how to determine those. So with this long derivation, we finally get something. We have beta k. With beta k, but we still have Hessian inside. It's like almost perfect, but we still have Hessian. But with everything that we derived earlier, we can actually, finally, we can get rid of those. So let me show you how we can get rid of Hessian. We need to use, here. So look at this one. From here, we can already replace something. We can, let me see. Not this one. Let's not use this one. So let's handle them separately. So the upper part and the lower part. Let's handle them separately. So the upper part equals to gradient k plus 1 Hasium k dk. Okay, and over here we know what is dk because xk plus 1 equals to xk plus alpha k dk. It's always like that. So dk equals to xk plus 1 minus xk over alpha k. So we can actually plug in. So this becomes gradient dot product Hasium dot product x k plus 1 minus xk, and we have a coefficient of 1 over alpha k in the front. Okay, so just plug in. Once you plug in, what would be the next? Because of okay, so the next thing I would like to use is over here. Yes, use this one. So because we had this equation earlier, so my Hasian matrix dot product, oh, let me just do this. So here is here, right? So I can replace Hasian dot product xk plus 1 minus xk. So I can rewrite this as dot product of k plus 1 minus fk. Yes. And this whole thing actually can be written as gradient f k plus 1 dot gradient f k plus 1 minus gradient f k plus 1 dot product gradient f. Okay, so over here you can already see how the upper part can be rewritten into a new form where you don't actually have Hasian. So finally, we get rid of Hasian in the upper part. So let's see if we can do similar things at the bottom. Okay. So for the lower part, dk dot product Hasium k dot product dk, and of course this is exactly the same. We do oh, hold on. Oh, this is not yet the final version. Hold on. It could be even cleaner. Hold on. So this guy could do something. So where do we have this guy? Using equation 3. Oh, okay. From here. Copy. Paste. From here. Okay. We could do something with this guy. So we know negative gradient, or we know gradient f and gradient f can be rewrite in different format. So this let me call this second term. So this second term, which is negative gradient f k plus 1 dot product gradient k, could be rewritten as gradient f k plus 1 dot beta k minus 1 dk minus 1 minus dk. We can do that. Okay. And over here, the reasoning. Okay? So if we do that, we can expand this whole thing. This is gradient f k plus 1 dot, beta in the front. Beta k minus 1 d k minus 1 minus okay, so gradient f k plus 1 dot dk is actually 0, but why? Because it was derived somewhere. Here. dk gradient f k plus 1 dot product equals to 0. dk dot product gradient f k plus 1 0. This one here. So this is actually 0. So that will make your derivation more cleaner. And what else? Okay, so we need to copy the whole thing. So copy and paste. So what we have so far, the second term, equals to this. This is what we call the second term. And we found it actually is this at the end, because the rest are 0, right? So from the previous page, we found, okay, the second term can be derived to here. Okay, so what about this one? Now we want to handle what's remaining in this second term, and we focus on this guy. So where did we derive anything about this guy? Yes, it's right here. We actually did some gradient calculation in the past. Okay, so recall this. And what we are going to use is actually the second part. The second part. Recall this one. Now, about this one, that's okay. So over here, I can plug in, right? So because we have this, so the second term becomes beta k minus 1 times gradient fk plus alpha k Hessian k dot dk minus 1. Okay? So what you will get in the end is actually just expand them. So beta k minus 1 times gradient fk dot dk minus 1 plus alpha k minus 1, beta k minus 1, alpha k. So now if you do this, dot product this, you actually need to flip it. So you actually get dk dot hk dot dk minus 1, right? Remember, Hessian is symmetric. So when you have matrix vector, this is a vector, dot product of this. This whole thing can be rewrite in the opposite way. So because this is symmetric, so this could be written as dk dot Hessian k. So we flip it to here, and then this is dk minus 1. Okay, so when you do this, this is 0 because of what? HK orthogonal. And this is 0 because of what? dk minus 1 dot gradient at k. D, if we have k minus 1 here, dot gradient at k. So just index minus 1. So same equation. So we finally found the second term of the upper part of beta is actually 0. Finally. So over here, we know the upper part of beta now becomes copy, paste. So finally, we only have delete. We only have this because the second term is 0. Finally, this is the upper part of beta right here. This has been derived into this long equation, and we took several steps to show this second term is actually 0. Finally, we get it. It's actually 0. Okay. So, how about the lower part? The lower part is dk hk dk. Is it? Sorry. So now we actually plug in. So beta k was gradient f k plus 1 dot hk dot dk and dk dot hk dot dk. So now we plot back. We actually have alpha k now at the bottom, dk dot hk dot dk, and the upper part is gradient f k plus 1 dot gradient f k plus 1. Okay, so now we have this. And so previously we actually didn't handle lower part. Let's get rid of this. Okay, we only handle the upper part. So but now when we plug it back, we now actually want to handle the lower part over here. So the lower part of this equation is alpha k dk dot hk dot dk. So what can we do with it? We can pre-multiply dk. Can we? No, we don't do that. We work on something else. We work on something else. Let me see which one. We work on we work on this one. The same equation. This one. But this time we want to handle let's handle this one. Copy. Okay, so let's handle cut. Delete. Okay, let's record this guy. And then that's why do we want to record this guy? Because it has dk dot product, Hessian k dot product dk over here. It's similar to this guy. So can we do a pre-multiply of dk and see what will happen? So we do this dk dot gradient f k plus 1. So this is something this is the part that we do pre-multiply. So what we will get at the end is dk dot gradient fk plus alpha k dk dot Hessian k dot dk. Okay, so we did pre-multiply, right? So when we do the pre-multiply of this equation, we have this, and you can see the final term right here is exactly the same as the lower part. So now we can rewrite the lower part as the this minus this. So and also, do you remember this is actually 0 because look at this, dk dot gradient k plus 1, dk dot gradient k plus 1. We've used this so many times. This is 0. So if this is 0, so this guy is this guy. So basically, this guy can be replaced by negative dk dot gradient k. So at the end, lower part becomes negative dk dot gradient fk. Okay, so beta k is now in a very clean form. Gradient f k plus 1 times gradient f k plus 1 over negative dk dot gradient fk. Okay. This is not yet the end. Not yet the end. So what can we do to make it even nicer? Do we? So from equation 3. Equation 3. Oh, okay. So that's keep this one. Copy. Paste. So we have this. And remember earlier we have another equation right here. Okay. So what is dk? dk was defined long time ago. dk was here. Yes, dk was here. So paste it here. So since dk equals to that, and so the lower part becomes negative gradient fk plus beta k minus 1 dk minus 1. Oh, there's a negative sign here. So the lower part again equals to this dot gradient fk. And this equals to gradient fk times negative. Positive, sorry. Times dot product gradient fk minus beta k minus 1 dk minus 1 dot gradient fk. Okay, so let me remind you the same trick again. This is dk minus 1 dot gradient fk. dk is minus 1 dot gradient fk. Also equals to 0. So this guy, this is 0. So finally, very final version. Very final version. The lower part, it becomes this. So final equals to gradient fk plus 1 dot gradient fk plus 1 over the bottom part is gradient fk dot. How simple is this? But how difficult was the derivation? We took around 1.5 hours to derive this. But we get such a clean equation at the end. Okay. So we need to recall the very first steps right here. Since we have we started with steepest descent, right? We have all these. Let me copy to the, and we want to put this beta k back to what we had earlier. So let's study this again. And I think we don't need this guy. Okay, so now we actually know this is negative k plus, what is beta? Beta, if we have minus 1 there, then we have k dot gradient k, and here become k minus 1. Because the index is minus 1. Okay? Multiply dk minus 1. So these is the final equation for steepest descent. Conjugate gradient. So in the first iteration, we start with steepest descent, and then starting from the second iteration, we use this equation to update our new variables. So the previous variable plus some alpha times dk equals to my new direction. And over here, new point, but what would be the new moving direction? The new moving direction will be the negative gradient plus some value here times the previous direction. And this value was derived by what we had earlier. So what were the assumptions? So the assumptions were, there are several assumptions. We use second order Taylor expansion, right? So basically, this only works if our function has only one minimum and looks nice. It's not like a wave, multiple minimum. Then this method doesn't work. Okay, so everything is based on. It's okay if it's not a second order form, because in every iteration, it will perform. So these calculations basically covers the knowledge of second order Taylor expansion. So basically, when you do this, you are still performing second order Taylor expansion at each iteration, but you just do it in a nicer way. You don't need to truly calculate second order derivative. So it's like in every new position, you still assume the local gradient look like a second order function, and then use it to find a new position. Okay, so this is the way for you to avoid Bayesian calculation, and also to know a better direction than steepest descent. Because steepest descent only knows this. It doesn't know how to make a directional modification. And this directional modification was derived based on second order Taylor expansion. So actually, it secretly hides information of Bayesian inside. Just use all those math that has been done earlier to get rid of the true calculation of it. And what was the assumption as well? Of course, we need the Bayesian to be positive definite. And of course, it's a symmetric matrix. Remember, in the one of the steps, we need some vector dot Bayesian to be reversible. So if we are able to reverse this in this way, then this Bayesian matrix has to be a symmetric matrix. Otherwise, you cannot do it. Okay. That's pretty much how this was done. And many of the derivation rely on the concept of Hessian orthogonal or Q orthogonal. So many of the terms could become zero at the end. Okay. And I believe you won't be able to know how to do it